to the bonding questions that I gave you the last day. So the first thing you were asked to do was distinguish between intramolecular and intermolecular forces. Now, let's remember, intramolecular forces are forces that hold atoms together within a molecule. So examples of those then would be ionic or covalent. Whereas remember all the E's, these are forces between molecules. So if you have A and a B here and an A and a B molecule here, they're the in-between forces, the intermolecular force, and examples of those would be things like van der Waals dipole-dipole forces or hydrogen bonding. The next part there then, you were asked to explain why the boiling point of oxygen is significantly higher than the boiling point of hydrogen, and they gave you the boiling points of both compounds. Now, what you need to see, both of these are non-polar. Okay, so they both have van der Waals forces between their molecules. So if I draw out an oxygen molecule here and another oxygen molecule down here, I can draw with the dotted lines then the van der Waals. If I drew a hydrogen molecule here, okay, and the neighbouring hydrogen molecule is there, and then I'm drawing the van der Waals between those hydrogen molecules. So they're both the same type of intermolecular force. They both have van der Waals between the molecules. So how do you explain that oxygen's boiling point is so much higher than hydrogen's? Well, you're going to have to say that oxygen molecules have more electrons. So remember, if you look up oxygen on the periodic table, you'll see 8 and 16. 8 is the atomic number, which tells you the number of protons, and remember that you have the same number of electrons if it's an atom. So 16 electrons here for the oxygen molecule, 8 and 8, and here you've 1 and 1, so there's only 2 electrons here. So the fact that you have less electrons, what does that mean? Well, it means that they can only, with hydrogen here, you have much weaker van der Waals. So you need to state that the van der Waals forces are weaker because of the fact that hydrogen only has 2 electrons. The temporary dipoles that can be set up in hydrogen are much weaker than the temporary dipoles that you can set up in oxygen, okay? Iodine, then you were asked why it's got a very low solubility in water, and you know that actually from the titrations that we were doing earlier on in the year. So if you look, you don't even have to look at the electronegativity value, sure you don't, because they're the very same, the difference is going to be 0. So the electronegativity difference is 0. Will that dissolve in a polar solvent like water? No, it won't. Remember our sentence, like dissolves like. So a non-polar substance will not dissolve in a polar solvent like water. Okay, so that's all you have to say there. When a charged rod is held close to a thin stream of water from a burette, the stream is deflected. So they asked you there to explain that. So what will happen, remember now, if this is your burette and you have water inside in the burette, now remember water is polar, so H2O, if I drew that there, so you have slightly negative oxygens and you have slightly positive hydrogens in here, okay? So if you bring a charged rod, it doesn't matter what charge the rod is. If the rod is positively charged, you're going to have the negative oxygens in the water attracting to the rod. If the rod was negatively charged, you'll have the positive hydrogens in the water attracting. So what do you have to say there? You're going to have to say that the water attracts to the rod because regardless of the charge on the rod, you will have opposite charges in the water that will attract to that rod. So that's all you need to say there. Question 2 then asks you to define electronegativity. So you'll say it's the relative attraction that an atom has for a shared pair of electrons in a covalent bond. And they ask you to draw water. So oxygen is in group 6. So 1, 2, 3, 4, 5, 6. And hydrogen has just the 1 electron. So remember to do the dot and crossing. Now look what you notice here. You have 2 pairs of electrons here that are not involved in bonding. So we call those lone pairs of electrons. What will they do to the bond pairs, these pairs here? They'll push them closer together. So you need to say that lone pairs have greater powers of repulsion or greater repulsive forces, pushing bond pairs closer together. So where, sometimes if you have 2 bond pairs, you might have a situation where it's linear, we have 180 degrees. But what has the 2 lone pairs done here? They have pushed those bond pairs closer together, pushed them down here. And actually now, look, if the closest angle there would be 104. And you just explain that answer by saying that the 2 lone pairs will push the bond pairs closer together, closing in that angle from 180 80, okay? And then finally, they had a similar thing there. Look about the burette. What would you observe if a charged wad was brought close to a stream of water? Same answer. So you're going to say the water attracts to the rod. It doesn't matter what charge the rod is. They don't have to tell you that. The water will attract to the rod because whatever the charge on the rod is, you have oppositely charged atoms in the water molecule that will attract to that. X2, look, the fact that it's X2 tells you that there are two bond pairs, okay? That the X is bonding to the Q is bonding to two X's. So you have two bond pairs. So what are your possible shapes? Well, linear, definitely anyway. But then if you think about that table in the revision book, what else do they have? Well, if you have two lone pairs and you still have two bond pairs here and here, your other possible shape would be V shape, okay? Question 4 then asked you to account for the difference in the shape of ammonia and boron trifluoride. Now, if you look up nitrogen in the periodic table, you'll see that nitrogen is in group 5, which means it has 1, 2, 3, 4, 5. Whereas boron, if you look that up, you'll see boron is only in group 3. So you only have 1, 2, 3 electrons there in the outer shell of boron. Now, I was looking at some of your work that you send me. I'm not correcting it because this is the idea behind the solutions, because it's really you must include the outer electrons. Look, so do you see the way some of you were just putting in the 1x there, but you must fill in the 7 electrons around the outer shell of fluorine when you're drawing the dot and cross diagrams, because fluorine's in group 7, so it needs 7 electrons in the outer shell there. Now, how will I account for the difference in the shape? So this one is pyramidal, this one is triangular planar. How do you account for the difference? You must mention the lone pair of electrons in ammonia pushing the 3 bond pairs closer together. So you're closing in that angle there to 107, whereas the angle here is 120. So the mention of the bond pairs pushing the lone pairs closer together would account for the difference there. Question 5 then, defining a covalent bond. That's fine if a covalent bond consists of shared electrons, distinguishing between sigma and pi. Now, there's only 6 marks going for that year, so I think all you needed to say there really is that sigma bond is formed from the head-on overlapping of orbitals, pi bond is formed from the sideways overlapping. Will you say p maybe? Will you say p orbitals? So sideways overlapping of p orbitals. Sometimes the p's in bold in the marking schemes there. It was that year. So head-on overlapping of orbitals is fine for sigma, but sideways overlapping of p orbitals. Now, if there was more marks going for that, also, you could maybe say that sigma bonds are stronger bonds because there's more overlapping between the orbitals. Pi bonds weaker. You could mention that point there too, if there was more marks going for that. Now, using a dot and cross diagram, now I'm after drawing ammonia already. You noticed that nitrogen was in group 5, so you draw 5 electrons in the outer shell there, and you X hydrogen's electrons. Deducting the shape, well, you're going to say that it's pyramidal, and explaining why the angle is 107, again, same thing. You're going to say that the lone pairs push the bond pairs closer together, closing in that angle from 120 to 107. Hydrogen bonding occurs between ammonia, and then it says, what are hydrogen bonds? So you're going to have to say that there are types of intermolecular, so they're intermolecular forces, okay, that they can occur in molecules where you have hydrogen bonded to FON, and you mention the interaction. Remember that the hydrogen is always slightly positive because these 3 are highly electronegative. So what does that mean? They'll always take the electrons. So you could say that you've got slightly positive hydrogen atom always bonded to slightly negative either fluorine, oxygen or nitrogen, and that then you're going to have interaction between. There are the hydrogen bonds, look there, the interaction between one molecule, say of HF, and the next molecule of HF, and you could always draw a diagram. Now, they asked you to show the hydrogen bonds between ammonia. They're intermolecular forces, lads, so you have to draw the hydrogen bonds between. So if I just draw 2 ammonia molecules there, I'm just drawing them this way because it's easier to show the intermolecular force, and then with a dotted line you're just going to show the interaction. So I could draw another one down here if I wanted to. Remember, the nitrogen is always slightly negative because they're much more electronegative. Nitrogen is much more electronegative than hydrogen, and then again you could show the hydrogen bonds between. Okay, now one would suffice there. Okay, that was it, wasn't it? Illustrate the diagram. Yeah, perfect. Okay, thank you.